Hello dear learners, this is Dr. Sedupati, Assistant Professor, Department of Computer Science with Artificial Intelligence and Data Science, Dr. SNS Rajalakshmi College of Arts and Science, Coimbatore. So today's topic will be process scheduling in operating system. Agenda for today's discussion will be process scheduling, scheduling queues and representation of process scheduling, and what are all the CPU switches and how the CPU switches one process from in and out of main memory to the central processing unit, and what is context switching. And here is process scheduling. What actually process schedule? It actually schedules or make a queue which moves each and every process from in and out of central processing unit core. The goal for the process scheduling is nothing but maximum CPU utilization and very quickly moving processes onto central processing unit core. And here is the types of scheduling queues. Basically scheduling queues maintains the processes in its list. Depends on the requirement and depends on the use. The scheduling queues are categorized into two types. One is ready queue and another one is wait queue. Ready queue having all the set of processes which resides in main memory and ready to move to execution into the CPU core. And wait queues are basically waiting for some other input output resources. Those processes are listed in the wait queues. Basically processes migrate among various queues, which means from ready queue to wait queue and wait queue to ready queue. And here is the syntax of how ready queue and wait queues are represented. In ready queue there is two processes, namely number 7 and number 2. We have discussed about PCB, which is process control block, in the previous videos itself. There are types of memories and types of execution code separated into the memory block, and there is a wait queue below, namely process control block 3, 14 and 6 and so on. And here is the representation of process scheduling. From the ready queue, all the processes are moved to the central processing unit core. Once a process received an interrupt or input output request which are under running in the CPU core are moved to the ready queues. Ready queues are basically four types. The first one is input output request ready queue, and the second one is time sliced or expired. Some of the process may be expired during any other uninterrupts, and some processor may require sub processes or maybe child processor or maybe interrupt signal. Those processes are moved to create child process as well wait for an interrupt event. These are all moved to wait queue status. Once the request or resource received, that particular process then moved from wait queue to the ready queue. Then automatically ready queue moves that particular process to the central processing unit core for the execution. Here is the CPU switch from process to process demonstration. The context switching occurs when the CPU switches from one process to another. Here in the left side of the diagram, process P0 is given, and in the right side process P1. Basically interrupt or system call occurs, the process P0 moved to save state into the process control block PCB0. During this situation, the PCB for the process 1 is in idle state. Once PCB0 in the save state, PCB1 moves to reload state and the process P1 move to execution. It is in execution. And after the execution, any system call interrupt occurs for the process P1. It then moved to the save state, which is PCB1 saved state, and both process becomes idle state. Once the P1 become idle state, the P0 process reloaded from the idle state to the save state for the execution. This diagram actually represents how CPU switches from process P0 to P1 and P1 to P0 vice versa. And here is the context switching explanation. When central processing unit switches to another process, the system must save the state of the existing process or the old process and load the already saved state of a process to the new process. This concept actually termed as context switching. Context of a process is represented always in the process control block, which we discussed in the earlier topic itself. Context switching time is pure overheaded. The system does no useful work while switching. And the more we discuss about this context switching, the complex of operating system and the process control block is that the longer the context switch, which operating system become more complex. The time component basically depend on hardware support. The switching time taken is based on the process speed and the RAM used in the particular hardware component. Some of the hardware component provides multiple set of registers per central processing unit. This type of context switching occurs very quickly, whereas multiple context switching loaded at once depends on hardware CPU works. And here is how multitasking happens in mobile system. Some of the mobile system in the earlier days, which is like iOS, allow only one process to run, others are basically suspended. What and why this happens is actually due to screen real estate. In a mobile, everything user can able to interact using only mobile display screen. So user interface limits iOS provides for a single foreground process which controls via user interface. There may be multiple background processors run in the memory, but not on the display and within the limits. The limits may be listed out like single processor or short task or receiving information from any other events or long running task and so on, or audio playback and some other downloading task which comes under background, which acts under background. Whereas in Android running machines or Android running mobile systems, foreground and background with fewer limits. Background processor uses a service to perform task. Services can keep running even if background process is suspended. Service has basically no user interface, so which uses actually a small memory space. So services can control simple parallel processes. So thank you for dear learners for your patient listening. We'll see you with some other topic in future. Thank you once again.